Since yesterday, I got a lot of questions about why I don't like eCash. And in this talk, I will simply try to explain why I do think ZK is superior to eCash and we need it and we should work on it. So our agenda is I will simply talk about history of both systems. Very briefly, I will talk about ZK proofs. I won't go into the mathematical details because I'm not a cryptographer and I'm not so comfortable about it. But I will talk about how to develop these systems and basically how they work. And then I will shortly talk about different proof systems, misconceptions about ZK proofs, eCash and ZK proofs on Bitcoin context, and then the applications, what kind of applications we can build with ZK, and I will just summarize everything. So with eCash, it's just repeated all the time in this conference, so mainly it's started developed around 40 years ago. It's get anonymity through blind signing. And actually, Bitcoin was a response to the limitations of eCash by simply solving the money component, because eCash didn't have some form of money, basically. You could use anything as money in eCash systems. And Bitcoin is designed in a way to create the money, but it makes eCash public, basically, so they have different trade-offs. But Bitcoin solves the money component of eCash, and this was the promise. With ZK proofs, actually, the history is starting in a similar years. Most people think that ZK proofs are something new, maybe like last 5 years or something, but in theory, it was around since the last 40 years. Actually, Halfini has a talk about ZK proofs in more than 20 years ago, showing that we can actually construct the ZK proof of a hash preimage, and this talk is actually recorded, and you can find it online. So this is more like the Bitcoin-related stuff in the ZK context. So we seen actually Greg Maxwell talking about ZK contingent transactions in 2011. And snarks are introduced 1 year after that. And snarks are basically the practical implementation of these ZK proofs that's been in theory for years. And a couple years after it, in 2016, the first contingent payment made on Bitcoin history, on Bitcoin mainnet actually. You can find the Maxwell's blog, I think on bitcoin.org or something, about this transaction. And then 2 years after it, we have Starks are introduced, and I will touch why they're important. So mainly, what we do with ZK is we just vouch on something is true without revealing anything about the statement itself. So it's a verifiable computation without disclosing any underlying data if you choose to do so. And it's been already used in blockchain context for years. And it holds more potential beyond privacy because it can bring scalability, trust minimization, and secure computation. So for terminology, we have a couple things here. The protocol is the system of rules that we define between the prover and verifier, and this is simply the thing that we follow over the process. Proof is the argument that establishing the truth of statement. Prover is the person that actually proves the argument, and the verifier is the person that actually vouches and verifies the given proof. And we can have some private inputs, which we choose them to be private, and this is agreed through the protocol definition. And we have public inputs and outputs, which both verifier and the prover can see. This is sometimes named as public inputs, sometimes as public output. It doesn't matter, but they're all public. So yeah, this protocol is between prover and verifier, and ideally these protocols are non-interactive so that we don't have to just do multiple hops. As prover, we just generate a proof, the statement, and then we give to the verifier, and the verifier verifies, so there is no interactivity between these two. And mainly, the prover has a prover key, private input and public input, and does the computation. And the verifier has a verification key, which can verify the proof together with the given public inputs. And this is the simply the diagram of the process. And if you visit zkintro.com, a third-party web page, I think it tells about ZK a lot, and it's very basic to understand. So this is a very basic snark circuit that's written in Circom. So it's a framework that you can write growth or Plonk proofs. It's very primitive, I would say, compared to the latest developments that I will touch on. But mainly, this statement says that I know a number that's, if you square it, it's equal to the square, but you don't reveal which number is it. So you can actually give a proof to someone saying that you know the square root of 25, but you don't reveal you know 5. And if you just larger the numbers, then it become much makes sense than just proving the 5. And this is a very simple syntax of how you can write this kind of ZK circuit. So we have different proof systems, and it's much more complicated than that. Some of them just overlaps because some proof systems use both of these properties, so it's just mixed. But previously, we were using snarks a lot, and that's why most people think all the ZK proofs need trusted setups, and that's not correct, basically. It changed a lot over the years. Plonk-based systems, they don't sometimes require trusted setups, and sometimes they're reusable. So you do single setup and use the same setup over the different circuits. And especially with Starks, now you don't have a trusted setup, which means it's fully trustless, that you can simply prove any statement, but the proof size compared to them are large. It's very scalable because you can just do unbounded computation, and the use cases are different, like the Starknet. I think Abdel talked yesterday about it. And Citrix, we are using Stark proofs in our ZK VM. So the main misconceptions I listed are just like the ones that I see online. I think these are very basic, but mainly people say that, I saw that one Bitcoiner tweet about it, you don't know what's being proven, so they can just simply trick you. And that's the whole point of ZKP. You know the protocol that's being proven, but you can choose not to know about inputs. I think the very basic example here is, it's not exactly a ZK proof, I will say, but simply digital signatures. You have private inputs, which is your private key. You have public inputs and outputs, which are public key and the message, and the proof is actually signature. So I know that I am signing with some algorithm, and I know that you are verifying with some algorithm, so we agreed on the algorithms, but I never share my private key with you, and you can actually trustlessly verify that I signed the message with my public key. So that's basically how all the ZK systems work. We both agree on some algorithm, but I choose not to share some information with you, but you can still verify this proof. The second I already talked is a trusted setup ceremony. So with some snark types, we need this trusted setup ceremony to generate an entropy, but it's still one of trust assumption. So the whole process is just relies on one single person, and if that person exists, they can simply delete their local key and make the process trustless. And if you are the one of them, the process is trustless for you. But more modern things like Starks, they don't require a trusted setup ceremony, or some of them just require single universal trusted setup ceremony. The third thing is, the circuit that I showed you before was just like an arithmetic circuit. It's still a DSL, but it's still complex. But right now we have different ZK VMs, and we can actually write Rust code or C++ code and generate a proof of execution for those code. I think this is a very big improvement, because if the tooling is developed enough, we can simply take Bitcoin Core and run in some ZK VM and generate a proof of execution without writing single line of circuit for our custom execution environment. So this is, you can see just a Rust code, regular Rust code, where you can prove the same statement with before, but it is much more readable because you know how to write Rust. So these systems are mainly working on instruction sets. For example, RISC-0 is one of them that also we are using. They have an arithmetic circuit, but it's written for the instruction set, the RISC-V instruction set, not a specific arithmetic circuit for your program. So we just compile our program into that instruction set and generate a proof of execution without dealing with anything regarding the arithmetic circuits. And the other thing is, ZK is not just about privacy. I would say mainly scalability. This is one of the diagrams that I used in my previous slides. Basically, if you do 2 transactions between Alice and Bob, and then Bob and Charlie, in regular L1, you have to record all these 2 transactions to get the latest state of the system. But with ZK, what we can do is actually, we can prove that these transactions happened correctly, and we can just record the delta of the transactions. So we don't just need to bloat the chain with unnecessary data, because the ZK proof actually vouches for the verification of the transactions. And if you just increase the intermediary steps, nothing changes on the data. If everyone just cycling the same UTXO, the change is just Alice is one UTXO down, and Charlie is one UTXO up. So you don't need to record everything. And actually, Ethereum ZK rollups work over this primitive. For example, a ZK sync, it's a ZK rollup on Ethereum. They use this thing called state diff. And basically, they can do 2000 TPS compared to the Ethereum's current 15 TPS limitation. And additionally, ZK proofs allows us to build trust minimized bridges because we can actually prove the consensus of some other chain, let's say Bitcoin's header proof, and we can verify that header proof into some other chain, which can simply say that this is the latest block hash of Bitcoin without relaying any oracle or bridge provider. And the last misconception is ZK proofs are hard to generate and it requires dedicated hardware. So this was the case maybe 10 years ago, but not now. So EVM, the virtual machine that we are also using, for example, there's a framework called SP1, similar to RISC-0, which allows you to prove the Rust code. And we can basically run a block with 16 transactions, and it only costs 20 cents to prove the execution of 16 transactions. So it's slightly above a cent per transaction. And EVM is one of the least optimized VMs to prove in ZK. If you build, let's say, a ZK optimized UTXO payment chain, it's called also Pay network on Ethereum. It's produced a local ZK proof on my iPhone in 2 or 3 seconds. And it simply says that I have a UTXO, I am now spending it to another blinded owner, and that UTXO actually exists in the current UTXO set. And this proof generation takes maybe 2 or maybe 3 seconds. So it's really fast. And they're also infinitely parallelizable, especially the Stark-based systems. So in here, you simply see that the RISC-0 frameworks benchmarks on hashing. And if I do 8 times more hashing, my time just increase 4 times. So we can do parallelization programs. We can simply divide the same program into multiple parts, and we can just aggregate them just like a Merkle tree. So we get a very good parallelization. And these benchmarks belong to a M2 Apple Mac. So it's actually really fast. So with eCash and ZK proofs on Bitcoin, so eCash works on Bitcoin today because Bitcoin's base layer supports primitives that eCash use. But the verification of ZK proofs is much more complex than verifying a signature. So the client-side validation of ZK proof is possible, and it was always possible. If you can embed a ZK proof into Bitcoin, then you can verify on client-side and make sure that the coin didn't double spend. This doesn't solve some problems, but I will touch. But it's not possible to do a non-optimistic verification of ZK proof on Bitcoin today with the current opcodes. So these CSV implementations actually inherit a lot of stuff from Bitcoin, but they lack the two-way peg mechanism. So the eCash operates outside of Bitcoin, basically, because Bitcoin is not aware of anything happening on eCash. It's just eCash is using Bitcoin as denomination, but it is the same eCash using dollars in the bank as denomination for Bitcoin, because there is no verification of what's happening on the other system compared to the ZK. So today, how we can verify the ZK proofs on Bitcoin is, the answer is BitVM. BitVM doesn't require any change to Bitcoin. And the idea is, let's just build a snark verifier script with the current opcodes. We know that it won't fit into a block. It's actually quite big, over a gigabyte right now. So we cannot just non-optimistically execute all the verification. But what we can do is, we can just divide the computation into, let's say, 1,000 chunks. And we can actually assign every input and output of these chunks using Lampert signatures or Winternitz signatures. And then some challenger can simply verify. So we actually verified the incorrect part of the ZK. And the Bitcoin can spend a UTXO based on the proof is correct or not. So it relies on one-of-n assumption. Honest participant should challenge the invalid proof. So it's trust minimized instead of being trustless. But the good thing is it's possible on Bitcoin today, and it's actually quite close to do the first proof of concept transaction on Signet. Stark proofs specifically rely on Merkle proofs and a couple other operations like multiplication. So if we have OPCAT, we can just do the Merkle proof verification, and this will reduce the size. It will even it's not possible today to do Stark verifier even with BitVM. without using snarks. But opget simply allow that. I think today there is one implementation that verifies a Stark proof, and it takes around 2 megabytes, so half of the block to do it. But this is still very unoptimized, and I do believe we can just get it under a megabyte. And the second option is a dedicated opcode for ZK proof verification, which needs another consensus, which proof system we are using. We can still choose something like gross 16 because almost all the proof systems can be verified inside each other. So we can do the wrapping, but we need to agree on. And the other option is we just implement a pairing opcode and everyone can build their own snark-based verifier. So for applications based on ZK is mainly, I can talk about shielded CSV. It's a very recent paper by Liam, Robin, and Jonas. So the idea is we should use Bitcoin for CSV basically. We should just embed a couple nullifiers to Bitcoin and verify that a coin is never spent. And the rest of the transaction data can flow between the sender and receiver using ZK proofs or any sort of proof. And the idea here is you get a lot of scalability because that data never hits on-chain. So the on-chain data per transaction is around 64 bytes, which I think gets around like 100 TPS today. And it's all fully private because you compress your transaction history using ZK proofs and send the proof to the other party. Another party can simply check Bitcoin, check your nullifier, and see that this transaction never gets spent before, but it doesn't know where this transaction came from or what are the history of the proofs. So it's actually fully private and possible on Bitcoin today. The only drawback is you still need some kind of two-way peg mechanism to peg Bitcoin. You can use stablecoins here, but for pegging, you still need to rely on BitVM or something like maybe federated bridge. But it's possible and it gets all the double spend guarantee of Bitcoin in this form. The second is a theoretical recursive ZK payment rollup. Basically, instead of passing the ZK proofs around, we can aggregate these ZK proofs all together. And Bitcoin can only see a single ZK proof, watching for maybe thousands of other transactions and a couple more data for commitments and nullifiers, similar to the shielded CSV idea. But in here, we can do pre-confirmations because these sequencers can actually get your proof, aggregate them, and post them on Bitcoin. And that time, you can actually trust sequencer to not reorg the chain, and you will get fully private transfers that's recorded on Bitcoin and get the double spend guarantees. The third thing what I'm building is Citrea. It's a general purpose ZK rollup, so it doesn't come with privacy by default, but it comes with a smart contract capability. And then you can simply copy everything that's been built on Ethereum and then run on Bitcoin. And these are all private applications: Tornado Cash, Railgun, Privacy Pools, Pay Network, Aztec, Polygon Maiden. They all built for Ethereum. And what we are trying to do is just mimic the behavior of Ethereum on Bitcoin so that we can get all these privacy applications without needing to port them one by one. And yeah, my summary is I don't think having privacy on Bitcoin today with eCash is bad, but I don't prefer using it. And I know many people, then they don't prefer using it if the amount exceeds a couple dollars. I do think we shouldn't call eCash endgame. I think it's a good primitive to have, but we need to work on non-custodial solutions instead of spending too much time on here. The second, we shouldn't shield how scalable it is because Visa and MasterCard is also scalable. And I also believe we should allocate more resources to potentially more trust minimize and non-custodial things. And we should find the optimal balance between the eCash solutions and trust minimized solutions. These primitives that I talked about, the shielded CSV, the payment rollup, this is not as scalable as eCash maybe, but we can find the optimal balance. Today on Citrea, you can pay Lightning invoice using atomic swaps, so we can actually build user experience where user can immediately swap between eCash and rollups, and they can just choose their own threshold for their custody safety. And yeah, that's all. Thank you for listening.
Thank you for the talk. When you say 100 transactions per second, or is a number that you said, Is it still correct to assume that for every transaction to settle, you have to wait for the next block, right? So when you speak of 100 transactions, you mean 100 people sending one coin once every 10 minutes?
Yes, that was also something that I told Jonas. It's not actually a TPS. If everyone's sending a different coin, yes, it is the TPS. But if you are spending the same coin, or if people are sending to each other the same coin, then you get less TPS than that. But that's not valid for this primitive. It's valid for shielded CSV. But in here, you simply have something called sequencer, which is the pre-confirmation, let's say, authority that can give pre-confirmations to you until
So
10 minutes.
Like a eCash mint preventing double spending, basically, again.
Yep, this is just like a single operator running an eCash mint, but it cannot double spend or mint money from thin air. It can only guarantee the ordering, and it can maybe reorg until the proof arrives on Bitcoin. But it cannot double spend you by just stealing your coins.
Okay, thank you. I assume it can collude with the previous owner, because I don't know of any other mechanism how you can make things faster than the Bitcoin blockchain.
Yep, it can. So actually, if you send the ZK proof and it's included in the chain, then yes, it cannot collude with the owner after that point. But in that 10 minutes, yeah, if the sequencer colludes with the previous owner, then you have to fall back to another mechanism, maybe like a decentralized sequencer.
Thanks, makes sense, yeah, thank you.
Thank you. I think one in the back.
One thing I would add is that you can actually combine these two techniques, right? So you can actually do pre-confirmations on the ordering of the nullifiers in the shielded CSV model.
That's also like something that we talked last week, and I'm not like sure if it is possible or not, because in here you actually aggregate the ZK proofs, so you can make sure that that transaction is like included or not. But in shielded CSV, I don't know how pre-confirmations would work, to be honest, because yeah, it can still collude with the previous owner and still in here too. But I feel like this mechanism is much better for pre-confirmations, because you can do mini blocks with actual proofs, and if you don't see your proof, you can make sure that something is going on, unlike here. But I think, yeah, there is probably some solution that you can do pre-confirmations on shielded CSV, but I don't know how.
Well, in shielded CSV, like your counterparty, they receive the proof directly from you, and then they're just looking at Bitcoin for the nullifier. Similarly, if you did shielded CSV in that model, the one you just flipped to, like the sequencer would just tell your counterparty, like, okay, the nullifier is in this like micro block at this, in this order, and then you send them your counterparty the proof, and then they can kind of
maybe
the verification. Another thing maybe worth noting is, like, if you want to increase the TPS of either of these models, then you can accept a stronger trust assumption by doing like off-chain data availability, like a Validium or something like that.
Yeah, if you don't put nullifiers on chain, then you can reduce the number a lot. And I also assume that these are like fully private solutions. So in the shielded CSV, there's something called inmax2, which is mentioned. It's not private, but you only need 4 bytes to put on chain to actually do a transfer. So it's actually much more scalable than these systems, but it's not private. For privacy, you need some kind of nullifiers on chain, so that's why it's less scalable. But yeah, that's also correct.
Yeah. Thanks.
I mean, when you look at the reality of BitVM based pegs, like the two important things I see to take into account are, one, the one of n trust model. So you still have intermediaries actually holding the coins. But in combination with that, the fact that users don't have a direct interface with that peg to exit non-cooperatively, that too is also a permission thing where one of the participants in it has to front liquidity, actually process that withdrawal. So at least with the current state of Bitcoin script, aren't these kind of systems just introducing needless complexity versus something like eCash, when ultimately at the end of the day, the two things that matter are still essentially the same. That there is some group that is custodying funds, and that to exit the system with real Bitcoin, you need to go through a permissioned process in the case of both eCash and rollups or other BitVM-based systems.
Yeah. Yeah, that's the limitation of BitVM2 basically. First, you need to have in the paper, you need to do a trusted setup, but you can be a part of it because it's pretty flexible. So we can just eliminate the trust assumption. The second thing is, like you said, we need one honest operator to front the liquidity. And then your federation simply becomes, let's say you have 10 operators, it becomes one of n threshold. So as long as one of these operators are honest, then you can get your money. But unlike in Fedimint, you have 8 of 10 or 7 of 10, which you need to trust more people. So I think if we can reduce this number to 1, it's still better. It's much more complex, I agree. But also, I think we should build for the future too. So we can, if we just implement these solutions, we can immediately switch to something cat-based in the future, if it ever comes. But even in the BitVM scenario, I still think it's better trust assumption, which is 1 of n compared to the T of n. Yep, I think that's all. Thank you, everyone.